I think, sorry to interrupt your conversations, but I think we'll go ahead and get started here. I'm Jonathan Koop. For those of you who don't know me, I'm faculty here in environment sustainability and also biology. And I work with John Mason coordinating the seminar series. This fall, we have sort of a themed series of 5 seminars. I'll tell you more about a couple of them in a minute, but on the theme of climate change, and particularly as focused here on the Gunnison Basin. So today we'll be conducting our own experiment of putting a bunch of warm, respiring people into a room for 50 minutes to an hour, and seeing if we can't raise the temperature here. So it's a real pleasure to welcome Dr. Scott Denning here, our first speaker of this series. He's the Monfort Professor of Atmospheric Science at Colorado State University. He leads quite a large research group using many kinds of observations and models to understand the metabolism of the Earth's biosphere. In addition to using global satellite imagery, his research has included extensive field work in the great northwoods of Wisconsin, the farms of Iowa, and the Amazon rainforest. He's also the Director of Education and Diversity for the Center for Multi-Scale Modeling of Atmospheric Processes, working to enhance understanding of global climate through K-12 undergraduate and graduate study, as well as informal education and public presentations. He's written over 90 publications in peer-reviewed climate literature, former editor of the Journal of Climate, served for 5 years as founding science chair of the North American Carbon Program, and he also takes special delight in engaging hostile audiences on the subject of climate change. So I'm encouraging your hostility. Oh, I know it's a tall order for this group, but
nobody has ever invited an audience to be hostile to me.
Welcome to Gunnison.
We're not going to be very good at it, I'm afraid. Certainly not in your, as compared to experiences speaking for the Heartland Institute. So, I'll just mention quickly his undergraduate degrees in geology from the University of Maine. He had a brief career in the oil industry, worked on biogeochemistry of high mountain watersheds for several years for his PhD studies at Colorado State University. He first joined the faculty at Donald Brent School of Environmental Science and Management at UC Santa Barbara in 1996, and then had the good fortune, I'm sure, to come back to Colorado in 1998, where he joined the faculty at his alma mater. So, how about a round of applause to welcome our speaker, Scott Denning, and then after we get done here, I'll tell you about some of the other top talks coming up later this semester, and I'm sure there'll be plenty of time for questions and answers in the session. Okay. Well, right. And just a quick note, we'll meet at if people are interested about 5 p.m. after the talk this afternoon, we'll meet over at the patio of the Twisted Fork. If anyone wants to come and talk more climate stuff, the brewery's going out as well.
So, I hope you don't mind, I'm kind of goofing around with this camera. This is a fun thing. As you probably figured out, what's with your glasses there? They're cold, is what they are, compared to your skin. What this is a thermal imaging cam. This is an instrument that's used a lot for finding problems with air conditioning and ventilation systems, finding leaky places in your walls that are letting heat through. What it's doing is it's taking a video in the thermal infrared. So we can see, of course, but what we see is basically reflected light, right? The light in this room is coming from little cans, around the edges, and it's coming in from the windows. By the way, notice the windows are nice and warm. See how that is? The windows are warm, but the wall is cold. You can see the studs in the wall. So what we're looking at here is not reflected light like we see with our eyes. This is actually the light that is shining from within. This is you that's making this light. This is not light coming out of a fixture and bouncing off of you and coming back to the camera. This is actually literally light that your bodies are shining. Yeah, every one of us shines, believe it or not, around 700 watts. And I know most of you are way too young to remember like 100-watt light bulbs, but back in the day we used to have 100-watt light bulbs, and each of us has like has about 700-watt light bulbs in us worth of energy that shines out just from our metabolism. Interesting. Can I have a volunteer? One of you people in the front row, please? Okay. could you film, or point this at me, and you focus it by twisting this thing and don't pull the trigger, who knows what would happen then. So see if you can point it at me. Okay, so here I am. And you notice that nothing up my sleeve. This is a black plastic trash bag, which I pulled out of that. I hope nobody used it. Okay, so let's see what happens. Point it at my face, please. And so notice that you can totally see through the black plastic trash bag in the infrared, right? The reflected light from the light cans bounces off, or doesn't bounce off, it just looks black. But the infrared light that my head is shining comes right through, and I go, ah! What I'm doing there. All right, now you're going to have to get up, and you have to follow me over to the door. Just for a sec. We're not going too far. So now I'm going to stand on the other side of the door, and just in case you get confused as to who's who here, I'm taking off my glasses, okay? So see how I look there? All right, I'm going to stand behind this door and see how I look here. So you can't see me through the door. Where your eyes can see through that glass just fine, the infrared is totally blocked by that piece of glass, right? Thank you very much. Yeah, good. So infrared light is a little different than the kind of light that we are used to in our daily lives. It passes through some things, it doesn't pass through other things. Everything in the universe is shining in different wavelengths, and at the kind of temperatures that we experience in the regular world, the kind of radiation that we shine, the floor, the wall, the ceilings, the desk, everything is shining in the infrared. So I'm going to talk to you today about climate change. I like to use 3 words that start with the letter S to talk about this. Simple, serious, solvable. It's kind of weird to say that climate change is simple. After all, I spent many years in school and been doing this for 20 plus years as a professional. If it's so simple, why am I still studying it? But the basic principles behind climate change are absolutely as simple as it gets, completely consistent with your everyday experience of the world, and that's what I want to talk to you about. However, it is actually quite serious. This is a serious deal. There are consequences if we don't take some action that will be really quite serious, especially here in the arid West, where we need water, and water is provided to us from mountain snowpack that runs down. This is a particularly vulnerable place for climate change. But I insist on not leaving you with the middle S. This is sort of one of my cardinal rules when I talk about climate change, is that the last word here is solvable, because we have the ability to deal with this problem, to solve this problem, and I will bring this all the way back around, and we will end with a message of hope, even if it gets kind of scary there along the way. So let's start with simple. Before we talk about climate change, we have to kind of get our terminology straight. Weather and climate. Weather outside today is lovely, I have to say. Very, very pleasant to come and visit Gunnison and find perfect weather and clear skies. And I suppose if I came back in February, I might have a different opinion. Who knows? So you guys know how to finish this sentence. If you don't like the weather, hey, somebody got that. That's pretty good. Everybody seems to think that they invented this phrase. I have lived a lot of places in my life, and almost everywhere I've ever lived, they use the same terminology. You don't like the weather? Wait 5 minutes. The weather is incredibly changeable. It's different in the morning and the afternoon. It's different on Tuesday and Wednesday. It's different from place to place, from time to time. Climate is not like that. If you don't like the climate, you're out of luck. If you don't like the climate, you have to move. Because really, climate is not changing from day to day. Climate is not changing from week to week. Climate is a function of where we live. Climate is place, okay? This is a picture of Fargo. I don't know, Fargo, you've probably never been to Fargo, but it's in North Dakota. It's cold there. I understand that Gunnison is often the coldest place in the lower 48 in the wintertime, and I suspect that Fargo bears is a close rival of Gunnison in terms of being the coldest place in the lower 48. Here's a picture outside of Phoenix. Phoenix and Fargo are different, you know? You really kind of can't get around it. The climate is different, and therefore the vegetation is different, and therefore the kinds of things people do for a living are different, and the kinds of cities that they build, and the kinds of houses that they live in, and the kinds of clothes that they wear, even the sort of culture. I mean, we all share a kind of globalized culture now, but I think almost everybody who's been to Phoenix and Fargo would agree that there's a little bit of a difference in culture between Phoenix and Fargo. And climate depends primarily on where you live. Latitude, duh, right? Phoenix and Fargo are different latitudes. Altitude, we know that real well in this part of the world, that as you go up higher in the mountains, the climate is colder, the climate is wetter, the climate is different. And it's not just different on Tuesday, right? It's really different. And it's going to stay different in these places because of the kind of place that they are. Climate changes very slowly, and climate, unlike weather, is very predictable. Now, that's an odd thing to say, because weather is not particularly predictable. When we have weather forecasts, we can predict the weather out a couple of days, 5 days, maybe, not 20 days, certainly not a month. And that's because weather it involves air masses moving here and there, changes in the wind, it's eddies in the jet stream, it's turbulent, it's chaotic. It's like trying to predict the pathway of an individual parcel of water down a whitewater river. Weather is very unpredictable, but climate is not. Climate is more like predicting that the water will run downstream, okay? So I can predict with great confidence that Phoenix will be warmer than Fargo this year. I can predict with great confidence that the average high temperature in Gunnison 3 months from now will be colder than the average temperature this month. And that's because it's determined by something that's predictable. We know the tilt of the Earth's axis and its relative to its orbit around the sun. We know the position of the orbit. We can predict changes in the day length, changes in the height of the sun in the sky. This is an extremely reliable prediction. I can predict very, very reliably things about the climate. Did you ever wonder why day is warmer than night? Did you ever wonder why summer is warmer than winter? Did you ever wonder why Phoenix is warmer than Fargo? It's all about heat, okay? I like to use in my classes a general form of what's known as a conservation law, conservation of stuff. The conservation of stuff goes like this. Stuff in minus stuff out is change of stuff, right? So that works for heat. Heat in minus heat out is change of heat. If more heat comes in than goes out, it gets warmer. If more heat goes out than comes in, it gets colder. The day-to-day changes with the weather are mostly about heat coming in and out the sides. Okay? An air mass comes in that's a little warmer than the air mass that went out. But when you talk about the Earth's climate, guess what? There aren't any sides. You live on a round ball floating in space. And no matter how you move the heat around sideways, nothing happens to the total amount of heat. You're just rearranging the heat on the round ball. The only way the climate of the Earth can change is to change the heat coming in and out the top. The top meaning the top of the atmosphere. Because the Earth is floating in a vacuum. And somewhere in the distant past, you learned that there are 3 ways to move heat around. There's convection, conduction, and radiation. Both convection and conduction take atoms. You have to have molecules to conduct heat too. But because the Earth is in a vacuum, there's no conduction of heat out into the vacuum. To do convection, you're actually moving warm stuff from one place to another. But again, because, thank goodness, there's gravity that holds the air down onto the planet, we're not going to convect any heat out of the planet. The only way that the Earth can change the amount of heat on the Earth is through radiation, electromagnetic radiation. Of course, the heat in comes from the sun. We all know this. You go outside, you feel it on your forehead, you feel the warm air. But if that was the whole story, the Earth would just get hotter and hotter and hotter, right? Because heat in minus heat out is a change in heat. And if the sun was the whole story, it would only be coming in. So we'd be getting hotter and hotter and hotter without bound. Well, we don't do without bound. There has to be something. And that's the thing that I showed you with the camera. The outgoing heat is invisible to our eyes, but completely visible to our scientific instruments. It's thermal infrared radiation. The Earth receives heat from the sun by radiation that's visible, but it gives heat back out to the rest of the universe in invisible parts of the electromagnetic spectrum that we were just looking at with that camera. So the overall budget is heat in minus heat out through the infrared. Now, to get the heat to go out, it has to pass through the air. And the air is made of molecules. This is probably the most sort of techie part of this talk, but everything's made of molecules. You, me, the rest of the room is made of molecules. 99% of the molecules in the air are made of just two gases. 99% of the air is made of two gases, oxygen and nitrogen. Roughly 80% nitrogen and 20% oxygen. Of course, that adds up to 100. I said it was 99%. O2 and N2 are both what we call diatomic molecules. They're two atoms of the same element glued together with shared electrons that constitute chemical bonds between the two halves of the molecule. And you learned somewhere along the line, electrons are negatively charged. You got electromagnetic waves going up through the sky, through the atmosphere. The magnetic fields interact with this cloud of shared negative charge that holds this molecule together, and it can actually accelerate the electrons so that the molecule can be thought of as vibrating, as stretching. Think of it as a little photon of outgoing energy hits this bond and starts it to vibrate like woo. It doesn't really make that sound. I made that part up. But when it does that, the energy that was going out through the atmosphere has now been converted into the kinetic energy of the vibration of the bond. And that molecule is now said to be excited, sort of anthropomorphizing the molecule. But the excited molecule can then de-excite by releasing a photon of the same wavelength, and that photon can go up, down, sideways, whatever, and the molecule will go back to its ground state. You'll like, woo, back to its ground state where it's not started. Okay, but because 99% of the molecules in the atmosphere are these symmetrical diatomic molecules, that's the only dance they know. It's the only way they can wiggle. It's the only mode of vibration available to two atoms on a single bond geometry of a molecule. There are two other gases in the atmosphere that have three atoms that are actually relatively abundant. There's other molecules too that have lots of atoms, but there's not very much of those gases. These two gases you've heard of before. This one's called carbon dioxide and this one's called water. And these are triatomic molecules, molecules with three atoms. And just like O2 and N2, carbon dioxide can absorb outgoing long-wave radiation, outgoing thermal infrared radiation. So just like, I only got the two hands, so please bear with me. I'll use my head for the carbon. Here's an oxygen, here's another oxygen. Like O2 and N2, I can go woo, 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 woo. But there's more. Because unlike O2 and N2, with that third atom, you can go bing, boom, bing, boom, bing, boom. And each one of these different wiggly ways to rearrange the geometry of that molecule will absorb a different wavelength of light, a different energy level of photon, and the absorption spectrum of CO2 gas is therefore much richer than the absorption spectrum of O2 and N2. That's what makes this a greenhouse gas. H2O is actually even better because it's bent. So you sort of imagine this kind of thing, and this kind of thing, and this kind of thing. So there's also kind of a concentration of positive charge down here, a negative charge up there on the oxygen. So it can to do flips like handsprings. Not going to try that here, that would be dangerous. But that's why these two gases are greenhouse gases. It's not because like greed is bad or capitalism or anything like that. It's just that they have 3 atoms. It's just bad luck for us that one of the gases that's produced when we burn coal, oil, and natural gas just so happens to have this rich absorption spectrum in the thermal infrared, very, very well understood. The physics of it is not that complicated, pretty easy to understand. That's what leads to the greenhouse effect. You've seen this diagram before. The sun shines on the ground, part of the sunlight reflects back off, goes back out outer space. The Earth warms up. The Earth has to radiate that heat back out. Some of the outgoing radiation does, in fact, get straight out to space, but most of it gets trapped in the atmosphere, either by CO2 and water vapor or by cloud droplets, which then re-radiate. Some of that radiation comes down. Actually, get this. We can measure it, right? I had this little infrared measurer out here before. You can run around and measure the heat coming down from the sky. And of course, during the day, most of that is sunshine. But at night, none of it is sunshine. And at night, we don't die by freezing to death. At least, most places. I understand, it might not be a good idea to run around in February without any clothes on. But if you measure, even here, even in February, if you measure with one of those thermal infrared measurers, the radiation coming down from the sky, and you add that up over the whole planet, believe it or not, we get nearly twice as much energy to warm up the surface from the warm sky radiating down on us than we get from the sun. Now, it all came from the sun originally, but a lot of that radiation is being trapped in the atmosphere and re-radiated back down. And quantitatively, this is a measurement, around twice as much of the heat at the surface comes from the part of the sky that is not the sun as from the part of the sky that is the sun. And of course, the reason is the sun's only up during the day, right? So for a big part of the 24/7, all we have is the warm sky. So this brings me to my assertion that greenhouse warming by CO2 is a matter of common sense. There are people in this room old enough to remember these things. This is an incandescent light bulb. This is a 4-watt light bulb. Back when I was a boy, these things were Christmas tree lights. This is my son. When my son was little, those things were night lights that they used to find the bathroom, right? You've seen these things, 4-watt light bulbs. So if you double the number of these molecules in the sky that's radiating photons down on us, it would add this much extra energy, 4 watts, to every square meter. This is actually pretty close to a square meter, this green thing up here on the board. Imagine that green thing down here on the floor, and imagine every square meter in this room having a 4-watt light bulb. Now, it's not a lot, right? It's only 4 watts. But guess what? It's not just this room either. It's the whole campus. It's all of Colorado. It's, my gosh, it's the whole planet. Every meter having a 4-watt light bulb on it. Now, if you did that, if you added 4 watts to every square meter of the planet and you left them on 24/7, 365 days a year for the rest of your life, that would make the surface a little bit warmer. And believe it or not, this has been known since before light bulbs were invented. Okay? The measurement of the absorption and emission spectrum of CO2 in the thermal infrared was first made by this guy, John Tyndall, in 1863. I said 1863, not 1963. During the U.S. Civil War, the absorption and emission of thermal infrared radiation by CO2 gas was quantitatively measured, wavelength by wavelength, and in 150 years since that measurement was first made, you can imagine that thousands of other laboratories have made this measurement all over the world. They all pretty much get the same answer. I mean, the measurements get better and better, the instruments get better and so forth. But in 150 years, nobody has ever been able to say, no, CO2 actually doesn't absorb or emit radiation. It really is only 3 watts per square meter. This is really, really well-established science. This is kind of like as difficult or controversial as the science that went into steam engines, which happened around the same time. So it's not like This was discovered in 1990 by Al Gore. This is something that's been around for a really, really long time. All right, brings me to what I call common myth number one about global warming. The myth, and almost everybody has this in their head, and they're wrong. But it's amazing how pervasive this myth is. The myth is that the reason we expect it to warm up in the future is because it's been getting warmer lately. And most people will start a global warming talk with a graph. And the graph shows that a long time ago it was cooler, and then it started to warm up, and lately it's been getting warm really quickly. Well, that's true, but that's not why we project a warmer future. You look at a graph like this, especially because somebody has put little colored lines on here, you get the idea that somebody's shooting an extrapolated line from this recent data out into the future and say, well, gosh, if that keeps up, it's going to get really hot. Well, fair enough, but that's not why we expect it to warm up. We expect the world to warm up because we know that when you add heat to things, they change their temperature. Okay? We know that the CO2 absorbs outgoing heat. We know that extra heat makes things change their temperature. It's exactly the same physics as putting a pot of water on the stove and putting a bunch of heat into it and watching it change its temperature. Now, there's a formal name for this principle. The formal statement of it is that the change in temperature is proportional to the change in heat. That's called the first law of thermodynamics. And it also goes back to the 19th century. But honestly, you have to be some kind of egotistical Victorian Brit to call something that fundamental the first law of thermodynamics. I mean, for goodness sakes, cave people knew this, right? They didn't call it the first law of thermodynamics. They said, ugh, hot. So when I say that it's simple to understand the science behind climate change, what I'm saying is that the reason we expect extra CO2 to warm the planet is because of the law of hot. All right, so much for simple. I want to tell you that this is also likely to be fairly serious. And I think it's especially likely to be serious here in the Mountain West. So this is kind of the sober part of the talk, the part that isn't as much fun. But I promise you that we're gonna get to happier stuff at the end. So how much warmer are we talking about? I mean, 4 watt light bulbs everywhere on the planet, that's just not that big of a deal, right? Of course, it depends. We don't know how much warmer it's going to be because we don't know how much coal, oil, and gas future people are going to choose to burn and put up into the atmosphere. If they choose to put very little into the atmosphere, it's not going to get that much warmer. If they choose to put a whole lot into the atmosphere, it's going to get a whole lot warmer. But that's not all it depends on. Maybe you don't know this, but there's a sort of a canonical number, a back-of-the-envelope number, and the number is 3. Okay? The rule of thumb is that for every doubling of the CO2, the world gets 3 degrees warmer Celsius. But when you look at these maps, these are projected warming by the end of this century under different emission scenarios. You notice they're not all the same color. Okay? So it's not like everybody gets 3. Some people get more than 3 and some people get less than 3. And the first thing you might notice is that the land warms up a lot more than the ocean. And that actually makes a ton of sense, because if you put a 4-watt light bulb on every square meter of the ocean, you're talking a lot of ocean. Did you know the average depth of the oceans is 13,000 feet? So the oceans are 13,000 feet deep. You put a 4-watt light bulb on 13,000 feet of water, it's not going to change that much, because it's 13,000 feet of water. There's a tremendous amount of heat capacity in 13,000 feet of water. So the oceans don't warm up as much. The land warms up much more. The next thing you might notice is that the southern hemisphere doesn't warm up as much as the northern hemisphere does. And that's also very easy to understand because the southern hemisphere is mostly ocean, the northern hemisphere is mostly land. So more of this heat capacity problem in the southern hemisphere. The third thing you might notice is that really snowy, icy places warm up a lot more than places that aren't snowy and icy. And again, we can understand this because snow and ice are bright and white and they reflect sun to space. And if you melt the snow and if you warm it up a little, you melt some snow and ice. And you melt some snow and ice and it turns from bright white to dark and it soaks up more sun and that warms it up a little bit more and then, so forth. So snowy places get more. So if you happen to live on land in the northern hemisphere where it snows, you get extra you don't just get the average global warming, you get extra global warming because of where we live. So if you look at the middle of North America, where we live, in a low emissions world, it's about 3 degrees of warming, and in a high emissions world, it's about 6 degrees of warming. Oh, but wait, those are Celsius degrees, because science. So we have to convert from Celsius to Fahrenheit to use the sort of units that we use in our daily lives. And so 3 to 6 degrees Celsius of warming is about 5 to 10 degrees Fahrenheit of warming. So we're looking at about a 5 to 10 degree amount of warming in the units that we're used to here in this part of the world, and much more in the Arctic, actually. So even 10 degrees of warming doesn't sound too bad, because after all, this is Gunnison. So I want to think about 10 degrees of Fahrenheit of warming in terms of climate as place. This is a map of average temperatures in the United States in Fahrenheit, and each color is 5 degrees difference on the map. So if you're going to warm up by 10 degrees Fahrenheit, you're going to move 2 colors on this map. And I put a dot in Grand Junction, and I put a dot in Denver, and I put a dot in Champaign, Illinois, where I happen to be giving this talk. And I'm going to move each dot 2 colors on the map, and you see that actually 10 degrees Fahrenheit is pretty far. 10 degrees Fahrenheit of change of place is like 600 or 800 miles further south. Now, actually, to be fair, there probably are places in places like Gunnison where warming by 10 degrees might actually be pleasant in some ways, but it's also going to have consequences in other ways. So you think about, for example, on the eastern plains of Colorado, where they grow crops, moving those croplands to central Texas or north Texas might actually mean you have to grow completely different crops. It might mean you have very different irrigation requirements. And if you're from around here, it probably isn't mostly about crops. It's probably mostly about forests and about tourism. I want to give you another sobering fact. This is 2 photographs of Shanghai in China. Shanghai is an amazing place. I went visiting Shanghai 2 spring breaks ago for work, and Shanghai proper, like in the city limits, there are 22 million people in Shanghai. And Shanghai has a whole bunch of suburbs, and you've never heard of any of the suburbs, and all of the suburbs have more than 10 million people in each suburb. So that's more than the number of people in New York City in each of these suburbs. Overall, Shanghai metro area, about 65 million people. And this is a photograph at a particular place. I walked this neighborhood. It's really kind of cool neighborhood. Right along the road is called the Bund, and it's a sort of 19th century European architecture. There's historical reasons why it has this look. This clock tower right here, I walk right by that clock tower. It makes like every 15 minutes the chimes, only it's not like the Big Ben chimes because it's these Chinese halftone kind of music that it plays. And this very old neighborhood, the one picture that you see when it goes down, that picture was taken of this neighborhood in 1991. And the other picture was taken in 2012. So this is just an amazing amount of economic development going on in China. And I put this up here to remind us that it's a big world we live in, and that there are an awful lot of people in this world. There are about 7 billion people on Earth, and there are only 1 billion of us. Okay? By us, I mean people who live in developed economies that use a lot of energy. 6 billion people in the world don't use a lot of energy. So population is growing, but not very fast. A lot of people, when I talk about climate change, will tell me, well, you know, the real problem here is population growth. Well, that's wrong. The population already exists. The human population in the 21st century is expected to grow by 30%. But the number of people that use a lot of energy is expected to go from 1 billion now to 4 billion by the end of this century, okay? It's not that those people are being born. It's that those people are dirt poor. And they're not going to stay dirt poor. And that's probably a good thing, right? We would be remiss to wish that billions of people would stay in abject poverty so that they could avoid releasing a huge amount of CO2 into the atmosphere. But those people are already here, and their economies are developing very, very fast. And we expect that the amount of CO2 emissions in this century will grow not by 30% to go with population, but by 300% to go with economic development. And it's a good thing. It brings me to common myth number 2. The myth is that when we reduce or stop burning fossil fuel, the CO2 will go away and things will go back to normal. And unfortunately, this myth is also wrong. Basically, the problem is that if China and India industrialize their economies with coal, which is their plan, the CO2 will not double. The CO2 will rise to 4 or 5 times the amount that was in the atmosphere before the Industrial Revolution. An enormous increase. And this is not a prediction. This is simply a what if done with a very, very simple calculation of the chemistry of the ocean. You probably can't even see this. Sorry. This is the year 1800. Here's 1900. Here's 2000. You are here. This is CO2 emissions rising to the year 2014. And here's where we think they're going by the end of this century with a business as usual, China and India industrializing with coal. So roughly 300% increase over the century. And I said to this simple chemistry model, what if we turn off the tap in, January 1st, 2100, Happy New Year, we're turning off the fossil fuel emissions. We're going to take 100 years to do it, and it's going to go to 0 and stay at 0 forever. Now, this thing goes out to the year 2300, which is ridiculous, right? I'm not actually predicting things in the year 2300. That's like way too far ahead. But if this were to happen, the CO2 in the atmosphere would rise, and then it would start to fall. But it would fall very, very, very slowly because it takes a really long time to turn the oceans over, to physically mix the oceans. The warm water's on the top of the oceans, the cold water's on the bottom, and it takes thousands of years to truly mix that water and allow that water to come into chemical equilibrium with the atmosphere. So basically, whatever happens over the next couple of human generations, the atmosphere will reflect that for many, many, many centuries to come. Not going to go away when we turn off the tap. We happen to live in a region that is extremely vulnerable to climate change. Did you know, maybe you didn't know this, there are 5 million people in Colorado now. Most of them do not live in the Gunnison Valley. Most of them live down in the Front Range. This is a picture of a new subdivision down in the Front Range. This is a map of Colorado, not a very easy to read map, but it's a map of the amount of precipitation that falls in a year in different parts of Colorado. The orange places are places where it rains 10 to 15 inches, precipitates 10 to 15 inches a year. If it were just the people who live in these orange and yellow places, if they could only use the water from the orange and yellow places, they wouldn't be here. We wouldn't have 5 million people in Colorado. The reason why we can sustain an urban population of so many millions of people and a huge agriculture industry in the state is because of these blue and purple places. You know what those blue and purple places are? The mountains, right? The mountains stick way the heck up in the air, and they grab every little water vapor molecule that goes by and turns them into snowpack. And when that snowpack melts, it runs down and fills our reservoirs, and we use that to support our cities and our agriculture. There's enough water, but there's not a huge amount of extra water to go around. And the snowpack holds more water than all the reservoirs in our state by a long shot. If we had to replace the storage capacity of the snowpack with new reservoirs to catch the runoff quick before it runs down the rivers, we'd be in a world of hurt. Because the snowpack is a free reservoir that dwarfs the size of our artificial reservoirs. The other thing that happens is that as you warm the air, the snow actually evaporates and sublimates into the air more readily so that you don't have as much water in the first place to put down. So it turns out that you can't really tell whether there will be more or less precipitation in a warmer world. We're pretty darn sure it's going to be a warmer world. We don't know whether Colorado will receive more precipitation or less precipitation in that warmer world, but we know for sure that more of that water will evaporate. in a warmer world, because warm air evaporates water quite readily. The other thing that's happened, not so much in this part of the state, but certainly in the part of the state where I live, is that insect pests have really taken off over the last decade, partly due to drought around the turn of the century, and partly due to warmer winters that have allowed both pine beetles and spruce beetles to overwinter and have an extra growing season of life cycle. I was just talking to Jonathan. We own this cabin up in Wyoming at 10,000 feet, and 90% mortality in the forest around my cabin of the trees, and about 30 of these dead trees were threatening to fall on the roof of the cabin, and I had to cut them all down. And, you know, I'm a college professor. I'm not real good at like wielding chainsaws at 10,000 feet. So, I mean, I guess I have a personal vendetta against these damn bugs. The other thing that we have is because there's more evaporation, there's more drought. Now, everybody pretty much knows that drought means no rain or less rain. But this is actually a map that's produced every week by the drought monitor at the University of Nebraska at Lincoln. Drought, according to people who monitor drought, is not just a lack of rain. I have to say this slowly, and I probably say it twice. Drought is the running sum of the difference between rainfall and evaporation. Okay? It's the running total of the difference between evaporation and rainfall. So either one of those two things changes and you change the drought. It can rain the same amount all through, but if you increase the amount of evaporation by 30%, you're increasing drought by 30% over time. So again, we can't predict changes in precipitation in Colorado very well, but we can predict changes in evaporation very, very well because they're directly tied to changes in temperature. The other thing that's really tightly tied to temperature, at least on a year-to-year basis, is fire. Fire in western forests is much greater in warm years than it is in cool years. There are three reasons. In a warm year, the snow melt comes earlier, so the forest has a longer period of summer during which time it's drawing water out of the soil. So it will tend to run out of water earlier in the like say in August than it does in a normal year. Secondly, because it's warmer, there's more evapotranspiration, so that the trees have more evaporative demand. They're drawing more water. And thirdly, the occasional really bad day. In the Front Range, we had just horrific fires in 2012, and both of those fires that burned hundreds of homes happened on these particular killer extreme days where the temperature was in the upper 90s, lower hundreds, very, very low humidity and wind. Those are the days that the fire gets out of control and winds up burning down into populated areas. All three of those things happen more in hot years. There have been more hot years, and in fact, the acreage of wildfire burn in the western U.S. has doubled in 30 years. If the China and India wind up burning all this coal to drive economic development, the air will get warmer, these extreme temperatures will happen more often, we will have more fires in the West. This is a significant impact to our way of life. The National Research Council has estimated the changes in wildfire in the western U.S. Under various temperature scenarios for the future. And this is western Colorado, 656% increase. I mean, perhaps say plus or minus what, because that's an awful lot of significant figures for this number. But something like a factor of 6 increase in fires in our part of the world, according to people whose job it is to try to figure this kind of stuff out. Economic development is also an issue here. Urban water use in Colorado is currently about 17% of the total amount of water in the state, meaning that agriculture gets 83%. I mean, agriculture is by far the largest user of water in the state of Colorado. Believe it or not, official projections are for 60% population growth in Colorado over the next, whatever that is, 30, 35 years, to 8 million people in the state of Colorado. This number is not big enough that you could cut the water use in the Front Range and accommodate 60% more people. You know, I got low-flow toilets in my house. I try to encourage my teenage son to take short showers. But even if we were to cut our water use by half, because we're only using 17%, that's not going to free up enough water for agriculture in the state. As we increase evapotranspiration, as we increase population in the cities, there's going to be more and more and more political pressure to divert water from rural areas into the urban front range. And this is going to have a significant impact on agriculture as well. Okay, so that's all pretty depressing. Let's talk about the third S, which is that this problem is solvable. This is not the end of the world. This is not a problem that we don't know how to solve. When I was a little kid, the total world economy put about 2 billion tons of carbon into the atmosphere every year, okay? This y-axis is billions of tons of carbon emitted by the entire industrial economy of the planet. 2 billion tons a year in the late 50s, up to, it says 8 here, but actually it's up to about 10 billion tons a year now. I have these colleagues, Steve McCullough and Rob Sokolow at Princeton, who did this calculation, so I want to acknowledge their slides. They said, what would happen if we just follow this path of emissions for another 50 years? We'll double the emissions, again, by the middle of the century, of carbon to the atmosphere. And they asked the question, what would it take, instead of following that current ramp, to follow this flat path of emissions towards the future so that the emissions just stay constant? Now that's not going to make the CO2 go away, right? I told you that even if you turn the emissions completely off, the CO2 stays in the atmosphere for 1,000 years. Rather, what they're doing is saying, somebody else 50 years from now can turn the tap off. We're going to stop opening the spigot wider and wider every year, and then I'm looking at you students. You guys can worry about actually turning the tap off. This is just a scenario. It's not a prediction. It's not a recommendation. It's a what would it take to go from this path down to this path. And because that's kind of a big thing to wrap your head around, they divided this triangular shape, the difference between current emissions and a flat emissions path, into 8 even-sized sub-problems, which they call wedges because they're shaped like wedges. And each wedge starts with nothing today and grows over 50 years into a strategy to avoid 1 billion tons a year of emissions 50 years from now. So these are what-ifs. So to put it sort of more bluntly, you start with nothing. 50 years from now, you've offset 1 billion tons. They use this unit, gigatons. A gigaton is 1 billion tons, like a gigabyte is 1 billion bytes. So a gigaton per year of less emissions. But McCullough and Sokolow made their job much harder. They said, okay, we're not going to consider strategies that involve technologies that are only on the drawing board. We're not going to consider things like fusion reactors, dilithium crystals, cold fusion, whatever. We're only going to look at technologies that we have in hand today. And even more difficult, they said, we're only going to look at technologies that are commercialized today and that are being commercialized at scale today. So only stuff that you could actually buy, that somebody's actually making profits selling the technology to somebody else. And they tried to rack their brains for 8 of these wedges. Believe it or not, they found 15 wedges, not 8, that use existing, commercialized, scaled-up technologies that we have in hand today that you've got to roll out over 50 years' time to add up to this stabilization triangle. I don't have time to go into all of them. Turns out, far and away, the cheapest solutions you can buy are efficiency wedges. So better insulation, better windows, better cars, better light bulbs, all that kind of stuff. Those things are way, way cheaper than, say, new nuclear power plants or carbon capture and storage, which are very, very expensive wedges. Nuclear power is certainly a way to produce a lot of electricity that doesn't put carbon into the air. That's an important wedge. You don't have to buy all of these wedges. You can argue over which ones you want. What you can't do is I'm only going to do one of them because it takes all sorts of different solutions here. I want to just give you an example of one of these efficiency wedges. There's an architect whose name is Ed Mazria, who, I don't know diddly squat about architecture, but I met this fellow. He gives a great presentation about the role of architecture in solving climate problems. He wrote a very famous article in an architecture magazine, cover article, like Architecture Digest. It says, "It's the architecture, stupid." He's poking his finger into the eyes of his colleagues and telling them that they have to, like, you know, come to the table and bring their best ideas on how to build buildings that use less energy. Mazria started I don't know what you call it, a nonprofit called Architecture 2030. He has since signed up every major commercial architecture firm in the United States and have signed this commitment that by 2030, they will not design a building that is not net zero energy over the life cycle of the building. This is amazing. Not just that it's going to like use less energy, but that including the cost of mining the materials, transporting the materials to the site, digging the pit, building the building, operating the building for the entire life cycle of the building, the net energy use of that project is zero. Wow! Every major commercial architecture firm in the United States has pledged to do this by 2030. Part of the upshot of that is these are projected energy use in buildings in the United States, projected by the EIA, the Energy Information something at the Department of Energy. Sorry, I'm authority. EIA projections of energy use. So this is projections out to 2030, made in 2005. The same organization looked at the same, at evolving data, new data, and made this projection in 2007, made this projection in 2009, made this projection in 2011, 2013, 2014. It's just in the last 5 years, the projected energy use by the building sector in the United States has decreased by 17 million BTUs, saving the U.S. economy $4.5 trillion over 35 years. Amazing. No, 25 years. Phenomenal saving. So there can be a sort of triple bottom line here. You can wind up emitting less carbon because you're using less energy and put money in your pocket. This is not necessarily a choosing between money and bad things thing. So why is there a toilet on this picture? It has been carefully estimated by people who know way more about this than I do. I mean, after all, I'm a scientist, not an economist. That the cost to the world economy of a complete changeover to a non-carbon emitting economy will cost about 1% of the world economy. Now, 1% of the world economy is a lot of money, okay? The world economy is estimated to be about $74 trillion a year in 2014. So 1% of $74 trillion is a boatload of money. But 1% of GDP. The last time that the world economy took on an infrastructure project that cost 1% of GDP was indoor plumbing. Okay? Right about 100 years ago, our ancestors knocked out walls and ran pipe up tenements in New York and London, and they dug up streets in every major city in the world, and they laid pipes, and they built toilets and showers and all that kind of stuff. Imagine the cost of this giant retrofit of very large existing cities with indoor plumbing. Now, by my way of thinking, that was really worth it. I love indoor plumbing, right? Who in their right mind would say, I wish the world economy was 1% bigger and I had to go poop in the street? You know, that would not be worth it. Besides that 1% of the economy didn't disappear. That money was spent by landlords and people who own these buildings, but it was spent paying plumbers, right? And plumbers wound up spending it on, workers, and they spent it at the people who make the pipes, and probably everybody who made money, either the plumbers or the people that make the pipes, turn around and spend it at the grocery store, and they spend it on rent, and they plowed it back into the economy. So it's an important feature of large macroeconomies that when you spend money, it's not gone. It's actually sort of a miracle. I mean, in the natural sciences, we think of like conservation of stuff, right? I talk to stuff in, my stuff out, I exchange the stuff. Economies don't work that way. It's a mystery to me. But you know, like if I sell you something for $1 and we both agree that it was a good deal, then there's more than $1 of value created. This is sort of the basic principle of capitalism, is that when money changes hands, value is created. That's actually a really important point here. So I want you to sort of do a thought experiment with me. I want you to take your mind back to the year 1800. And I don't know if any of you study history. Just give you some buzzwords about the year 1800. Thomas Jefferson was president. Napoleon was storming across Europe. Ben Franklin was playing with kites and keys and stuff like that. Imagine you're in charge, emperor of the world. I guess Napoleon, thought he was the emperor of the world, and along comes his they didn't have energy ministers back then, but his advisor and said, "I got the correct idea for you, Your Excellency. We're going to dig 8 billion tons of carbon out of the ground every year, and we're going to build pipelines and super tankers and railroads and highways, and we're going to deliver that stuff to every 7-Eleven street corner on the planet, and cars. We're going to take rubber tires and stick them on the carriages and put internal combustion engines on them. And we're going to lay out 10 million miles of paved freeways, and we're going to drive real fast, and we're going to take that thing Ben Franklin does with kites and keys, and we're going to centralize it, and we're going to run separate little copper wires to every house on the planet. They're going to have TVs and stereos and all kinds of cool stuff." And if Napoleon was smart, he would have had an accountant who would be tallying up the cost of 10 million miles of freeways and how many billions of miles of copper wire. Oh my gosh, no way. You can't afford it. It turns out that the amount of money that was spent building this world that we have inherited is more than the total amount of money in the world in 1800. Whoa, where did they get that? How did they build this without going completely broke? Our ancestors did this. They actually spent every dime of global GDP for 200 years building this incredible system that we got. But it didn't just cost them every dime, it created every dime. That's how capitalism works, is that by buying and selling stuff from each other, we build up this great big system. And now our kids get to do it again. They get to build the world of tomorrow out of the stuff that they inherited from us, just as we built our world from our ancestors. I ask you to choose your future. There's a whole bunch of people in academia, even people that I like and people that I know, that sort of sign up for this version of an understanding of history that basically says that the wealth of the world is extracted wealth. Okay? There's value. There's inherent value in a lump of coal. And we dig that lump of coal out of the ground, and we bring it to the surface, and we sell it to somebody who's going to burn it and make energy, and they're going to sell the energy to somebody who's going to use it to make a product. And there's this sort of fundamental unit of extracted wealth, and then there's a multiplier effect that spreads it out to become a $72 trillion per year economy in the planet. And it kind of rings true, makes sense. I mean, there certainly is value in stuff that we dig out of the ground. But fundamentally, this is an incredibly pessimistic view of human history, of the meaning of civilization. The idea that we depend entirely for our existence on stuff we dig out of the ground. Because if it's true that we run out of that stuff, the house of cards comes collapsing down on us. And our descendants, inherit a pile of collapsed cards. I prefer this one. The modern world, the wealth of the world, doesn't come out of the ground. It comes from us. It comes from ingenuity and hard work and the sweat of our brows. And that as long as our kids can be as brave and creative and ingenious as our ancestors were, they're going to be okay. Thanks for your time.